Let's take another look at LU decomposition, the recursive nature of it. The concept that a 4 by 4 matrix is reduced to a 3 by 3 is reduced to a 2 by 2 to accomplish the elementary row operations to codify LU decomposition. Let's think about what LU decomposition means. LU decomposition means lower triangular times upper triangular. And if I'm trying to realize the black matrix, and I'm going to use a lower triangular matrix times an upper triangular matrix, then it's required that I represent the first column of my matrix product in the first column of L, and I represent the first row of my matrix product in the first row of U. Think of these as the L and U under construction. I mean, the concept is a 1 with the zeros in the row sweeping across this is the only way to produce 1, 2, 1, 2, my first row. Or a column with a 1 and zeros below, that column is the only way to sweep across this matrix and produce 1, 2, minus 1, 1 in the first column of my product. Now, bearing in mind that what I'm doing is elementary row operations to produce the U, the inverses of them are coded in the L. Now I'm going to do the elementary row operation that would create these 3 zeros. That is, multiply row 1 by minus 2 and add it to row 2, multiply row 1 by 1 and add it to row 3, multiply row 1 by minus 1 and add it to row 4. When I do that, this is the result. So I have minus 2 times this 0, negative 6, negative 1, negative 3. Adding first and third rows, 0, 3, 0, 4. Negative 1 times first row plus fourth will give me 0, minus 3, 0, minus 3. Now I emphasize in red that I've reduced to a 3 by 3 matrix. And really, all I need to do is LU decomposition on the smaller animal. So we accomplish LU decomposition on larger animal by whittling it down into progressively smaller matrices, smaller animals, if you like. So produce these red 3 by 3 matrix. I must have the first column represented in the first column of my L. But I do that respecting the elementary row operations. I divide by minus 6 3 times. Negative 6 divided by negative 6, 1. 3 divided by negative 6, negative 1 half. Negative 3 divided by negative 6, 1 half. The idea is I'm going to multiply this row by 1 half and add to get rid of this 3. I'm going to multiply this row by minus 1 half and add to get rid of this minus 3. But when I bring those elementary row operations over to this side to record an L, that means I'm inverting the elementary row operations. This will put a minus 1 half and a 1 half here. Across the top, as I do the LU decomposition, I just keep the minus 6, minus 1, and minus 3. These are the red numbers you see. Now I have to perform the elementary row operations that I just spoke to you. 1 half times this plus this, 0. I'll fill in zeros as I go. Minus 1 half times negative 6 plus negative 3, 0. But 1 half times negative 1 plus 0 is negative 1 half. And negative 1 half times negative 1 plus 0 is positive 1 half. 1 half times negative 3 halves, plus 8 halves is 5 halves. And negative 1 half times negative 3 halves, minus 6 halves is negative 3 halves. Now, elementary row operations produced the red matrix, turned it into this smaller green matrix. Well, of course, I'm working on the whole 4x4 matrix, but I'm not doing any actions where these zeros occur. So now I have to represent this green matrix, LU decomposition. And now you know the speech. I'll take -1/2 divided by -1/2 and 1/2 divided by -1/2. That's what must occur in the first column. And what must occur in the first row is -1/2 and 5/2, the first row of this green thing that I'm building. What I do is say, when I do row reduction on this 2x2 green matrix, I'll do 1 times this row added to this row, which will put a 0 here, and 1 times this row added to this row will put a 1 here. Of course, I'm still working with all the previous zeros with the full rows, but I'm focusing on whittling down this matrix. Now I come to the last stage, and I have a 1x1 matrix that I want to write an LU decomposition of, if you allow me to say that. That's a little bit of overkill. I'll take this number divided by itself, that's 1, and write it there. And then I'll repeat this number as the row of the 1x1 matrix that I put in the U. I think that's a little bit silly, but I'm demonstrating how I go from 4x4 to 3x3 to 2x2 to 1x1. Now when you multiply these matrices right here, L times U, you can see that I've produced the original matrix A. You also get that side benefit of determinant. This is determinant 1. This is determinant 1, -6, +3, 1. This matrix has determinant 3. This matrix has determinant 1. So this matrix has determinant 3. It would take me a minute or two to expand it, but try it and see if you don't get 3.